Have you ever just looked around at everything and wondered if it's all really real? Or if maybe, just maybe, this whole three-dimensional world we live in is some kind of complex projection, an incredibly detailed hologram? Now, that might sound like something straight out of science fiction, right? But believe it or not, it's one of the biggest, most profound questions in physics today. And the biggest clue we have? It's hiding inside the most mysterious objects in the entire universe, black holes.
To get our heads around this, let's start with a little thought experiment. Imagine you have a book, say your favorite one, and you toss it into a black hole. Now, the book itself? Yeah, it's gone, obviously. But what about the information inside it? Every single word, every letter, every idea, is all of that just blinked out of existence forever? How you answer that question actually puts you right in the middle of a huge cosmic battle.
See, on one side, you've got Einstein's general relativity. This is the theory that describes gravity, black holes, the whole grand scale of the cosmos. And according to Einstein's math, once that book crosses the event horizon, that point of no return, it's gone. The information is completely, utterly destroyed. But on the other side, you have quantum mechanics. This is the rule book for the universe at the tiniest, weirdest scales. And one of its most sacred, fundamental laws is that information can never be lost, ever. It can get scrambled, sure, rearranged, hidden, but it can never ever be totally erased. So these two pillars of modern physics give us two totally opposite answers.
And this clash of the titans, well, it leads us straight into our first big idea, a deep, really unsettling problem that we call the black hole information paradox.
This whole paradox really blew up thanks to Stephen Hawking's work back in the 70s. He figured out that black holes aren't perfectly black after all. They actually leak. They evaporate very, very slowly by giving off this faint glow we call Hawking radiation. But here's the kicker. His calculations said this radiation was completely random. It had zero information about what fell into the black hole in the first place. So as the black hole shrinks and eventually disappears, all the information inside it just vanishes with it. And that is a massive violation of quantum mechanics. This isn't just some small disagreement, you know? It's a sign that our most fundamental laws of physics are completely breaking down.
So, how do we fix this? Where do we even start? Well, the very first clue came from a place nobody expected. It has to do with a really, really weird property of a black hole's surface. To get what this clue is, we have to talk for a second about a concept called entropy. Now, you probably heard in science class that it's a measure of disorder, and that's true. But in physics, it's also a way of talking about information. Think of it like this. The more ways you can arrange the atoms in something, the more information it takes to describe that specific arrangement. So when we talk about a black hole's entropy, what we're really talking about is its information storage capacity. How much can it hold?
And this is where things get completely bizarre. I mean, you'd expect that the amount of information something can store would be based on its volume, right? It's three-dimensional space. More volume, more storage. Makes sense, but what Jacob Bekenstein and Stephen Hawking discovered was that a black hole's total information content, its entropy, is proportional to its two-dimensional surface area, specifically 1/4 of the area of its event horizon. Just let that sink in. All the information about a huge 3D object is somehow written on its flat 2D boundary. This went against all intuition. It just felt wrong.
And the crucial thing here is that this wasn't just a clever analogy. As Bekenstein himself pointed out, the entropy from thermodynamics, the physics of heat and energy, is basically the same thing as the entropy from information theory, the world of bits and data. This meant the link between a black hole's surface area and its information content was real. It was a quantifiable physical fact, and it was a huge clue that maybe the universe stores information in a way we never, ever imagined.
So what on earth could this mean? This one strange fact about surface area? Well, it led physicists to a conclusion so radical, so mind-bending, it sounds like it was lifted straight from a movie. They called it the Holographic Principle.
Here's the core idea. If all the information about a black hole is somehow encoded on its 2D surface, then maybe that's true for everything. Maybe our entire three-dimensional reality is nothing more than a holographic projection. All the information that makes up you, me, and everything we see is actually stored on some vast, distant, two-dimensional surface. It's just like the hologram on a credit card, right? That's a flat, 2D surface, but it projects a full 3D image. The holographic principle says our whole universe might work the same way. The 3D world we experience could be an illusion.
Now, this wasn't just some wild guess people threw out there. It was built up piece by some of the smartest people on the planet. First, Gerard Hooft proposed it back in '93 as a potential way out of the information paradox. Then, Leonard Susskind took that idea and showed how it could work within string theory. But the really huge breakthrough came in 1997 from a physicist named Juan Maldacena. He discovered a precise mathematical dictionary that could translate the physics of a 3D universe with gravity into the physics of a 2D universe without gravity living on its boundary. This showed the holographic idea wasn't just a cool metaphor, it was mathematically solid.
Okay, so we have this powerful holographic idea. But how does it actually get the information out of the black hole? For decades, that was still a huge mystery. The final piece of the puzzle, though, is a pretty recent breakthrough, and it has an amazing name: Entanglement Islands.
All right, so here's how the solution works. It turns out that as the black hole evaporates, the Hawking radiation escaping from it becomes quantumly entangled with a region deep inside the black hole's interior. This region is the island. And what entanglement means here is that the information in the radiation outside the black hole is basically a perfect holographic copy of the information that's inside the island. They aren't two different things. They're two different descriptions of the exact same information.
So let's just walk through it one more time. First, you had Hawking's original math, which was missing this key ingredient. It gave you an entropy that just grew and grew forever, which makes no sense physically. But now, with the new island formula, you include this entanglement island in the calculation. And when you do that, bingo, you find the information isn't lost at all. It's perfectly preserved, encoded in the escaping radiation, because that radiation is a hologram of the island. This solves the paradox and gives you the correct page curve, which shows the entropy rising and then falling again, exactly like quantum mechanics says it should.
I know this is a pretty abstract idea, so this image can help. It's a way to visualize the math from string theory. Just think of that red line as a simple 2D surface. The incredible thing is that the math shows this surface can contain all the information needed to fully describe the entire 3D volume that it surrounds. It's a real mathematical example of the holographic principle in action, showing how a lower dimensional boundary can encode a higher dimensional space.
So the paradox is solved. The information is safe. Fantastic. But the implications of how we solved it? They're staggering. And they force us to completely rethink what reality even means.
The consequences here are just, wow. If the holographic principle is right, it means space and time are not fundamental. They're not the basic building blocks of reality. Instead, they emerge from something deeper, a fundamental layer made of quantum information, of quantum bits. Gravity itself might not be a fundamental force, but just a sort of side effect, like the way temperature emerges from the jiggling of atoms. And it means the solid, three-dimensional world you and I experience every day could, in a very real sense, be a hologram projected from those bits.
Which leaves us with one last, absolutely awe-inspiring question. We started this journey with a book falling into a black hole, and we ended up with the idea that our entire universe is a projection. If that's true, if our reality is just one grand cosmic hologram, then what or where is the projector? What's the surface it's all being projected from? And what's running the show? That is a question we are only just now beginning to figure out how to ask.